Right, so this is the last lecture in the series. So from next week onwards, it'll be just revision and problems classes. Right. But so the last thing we have to do is just say a little bit more about the ordinal definable sets that I was going through, and then we'll be done. So let's recap a little bit. We said that the set Z was ordinal definable basically if it was the unique solution to a formula with ordinal parameters. If for some phi and some alphas, Z was the unique, was the only set held like this. Okay. So being ordinal definable, this is equivalent to saying that it actually was definable by a formula without any parameters over some v beta. And that's what def 0 does. It says definable by a formula with no parameter over v beta here. So in some sense, you could say we can define it without using the ordinal parameters, but of course there's an ordinal being snuck into here, this beta. And the set here, v beta, is being used. But the idea is that now this is something we can define in our language of set theory, right? Whereas this was an informal definition, which we couldn't. So what else did we see? We saw that there was a well order, a globally defined well order of OD. So it has a definable well order. Right? This was theorem 422. And this was theorem 421 here. And we saw various other facts, right? We saw that L was contained in OD. And we were looking at then the definition of HOD. Z was hereditarily ordinal definable. Means that it is ordinal definable and its members are ordinal definable and so on. So it's ordinal definable and its transitive closure is contained in the ordinal definable sets. So particularly this is going to mean that, sorry, Z, this is going to mean that HOD is a transitive class. It contains all the ordinals because OD contains all the ordinals. And they are, again, contained in OD. As the ordinals are contained in OD, then the ordinals are contained in HOD. And there's one way of thinking about what HOD is, sort of an alternative expression for it. This is exercise 418. So Z is in OD, and for all Y in Z, Y is in HOD. So this is part of 418. This was, it also said show power set of omega intersect. OD is the same as the power set of omega in HOD. Okay, I left that for you to do, but actually why don't I do this one here? Because that'll help the discussion along. So what is one saying? Basically, sometimes this is easier to verify. If you want to see that something is in HOD, you just see that it's in OD and all of its members are in HOD. But this also sort of encapsulates the idea about something being hereditarily ordinal definable. All its members have to have this property. So it's just an exercise in definition changing, right, here. Z is in HOD. If and only if, and now I write this definition here, this is by definition. TCZ is contained in OD. So I just write out the definition of TCZ. Z together with the union of all the transitive closures of its elements is contained in OD. So this is just this. So this is equivalent then to Z is in OD. And I'll just kind of rewrite this here a little bit. I look for all Y and Z. Singleton Y should be contained in OD. That ensures that Z is a subset of OD here. And then the transitive closure of Y here. So I don't want to put the bracket here. I want this to be an OD. Right, I mean, this part is just saying all the members of this set are in OD, but that's what this is. Right? There's a simpler way of putting it. And now we are back to saying Y is in HOD. So later, when we come to just look at a few things or some few things in an exercise, it's to verify something is in HOD, it's enough to know it's ordinal definable and all its members are in HOD. So we thought that HOD, as I said, was a transitive class, contains all the ordinals. We were in the middle of showing that this makes HOD an inner model. So this was just in a shorthand for saying that HOD is transitive, it contains all the ordinals, and the axioms of ZF all hold in HOD. And we'd done some of the axioms, but not all of them. So again, this is one of these slightly sort of lengthy theorems where you justify all the axioms holding inside some structure. So we were trying to show that ZFC, in fact, held in HOD. So let's see. I think we'd already done, I won't go through the ones we already did. We did empty, extensionality, pair, union. And we were in the middle of doing the axiom of power. Not sure whether we'd not sure whether we'd finished that here, but let's in any case reboot it. Suppose X is in HOD. We want that the power set of X in HOD is a member of HOD. And I mean, it's enough to see then that power set of X here is in an element of OD here. So let's see, I see in the notes I said by the last exercise. Power set of X intersects HOD. Because if I know that X is in HOD, right, then all the elements of X are in HOD. So all the subsets of X are in HOD. Right? Well, all the subsets of X are the members of the power set of X. Right? So all the members of this set, right, here, right, sorry, all the members of this set, right, I should be pointing to this one, all the members of this set here, right, these are subsets of X. And if X is a member of HOD, HOD is transitive, so it's a subset of HOD. So all of its elements are members of HOD. So all of its subsets are members of HOD that are in here, right? So if HOD thinks that something is a subset of X, right, it's got all of those elements in that subset in there. So I'm just appealing to this here, right? I've got a certain thing which I want to be in HOD. I know all of its elements are in HOD, so all I have to do is show that the thing itself is in OD. Right? And the thing I'm talking about is this. Right? So by the last exercise, part 1, we'll have that is in HOD. So it's this epsilon here that we need to justify. This is just the definition of the relativization. Okay. Power set of X intersect HOD is the power set of X intersect OD. If Y is a subset of X, okay, then Y in OD implies Y is in HOD. Right? So this was what I was fumbling around with in the last exercise. So it's getting repetitive here. So it suffices to show power set of X intersect OD is a member of OD. Because these are the same. So this looks like a simpler condition. Okay, so let gamma 0 be the rank of X. Then in V, what do we have? The power set of X intersect OD is certainly going to be a subset of V gamma 0 plus 1. I think that's a little misprint in the notes there. It says V gamma 0. But if X is a subset of V gamma 0, then the subsets of X are going to be elements of the next level. Yes, so this should be V gamma 0 plus 1. So phi sub OD was the ordering that we had on. Sorry, let me just check. No, that wasn't phi sub OD. Just trying to see where this phi sub OD occurs. I wanted to refer back to it. Let phi sub OD be as above. think this is just the formula of 421. There it is. So phi OD said that being in OD is expressible in a first order way. X is outright definable over this V beta. So this holds if and only if Z is in OD. Right, as X is in OD, some formula psi and beta 1 up to beta m, so that X is uniquely definable, just that psi holds of X and the betas. Okay. So now use the reflection theorem. On phi OD and psi at the same time. So we can find some gamma 1, which is bigger than all of the betas, and gamma 0. And now I've got, if Z is the power set of X intersect OD here, if and only if reflecting to gamma 1, what holds in gamma 1, there is an X, so it's the psi X beta vector. So gamma 1 is big enough to see, right, the X, that's the unique thing that makes psi true. So X is there inside V gamma 1. So this exists, X is picking up this gamma 1 here. And then Z is the set of Y's that are in OD, and Y is a subset of X. So what we've got is then this V gamma 1, right? Over V gamma 1, I can define this here. Right? I define the unique X, and then I've got this Z here, which defines the subsets of X that are in OD, therefore in HOD. So what have I got? I've now got then, I can define over V gamma 1, right? This particular set here. So what I've got is a definition of Z, right, using these ordinals beta and gamma 1. So we have a definition in V of power set of X intersect OD as the unique Z satisfying this formula star. Using the ordinals gamma 1 and beta vector. So Z is in OD. Okay, so it's a little bit involved, right? Admittedly, right? Okay, axiom of separation. So I've got A, so class term. And take a set in HOD. So what we're after is that A relativized to HOD intersect X here. This should be a member of HOD. So what does A look like? Right, so A is the class of Zs such that some phi Z Y vector holds, right, where Y vector are just parameters in HOD. Okay, this is a single formula, so I can find from the reflection theorem arbitrary large gammas which are reflecting for phi. Find a sufficiently large gamma reflecting for phi. And the defining formula phi OD for OD. And with AHOD intersect X being in V gamma. So this is in V. We don't know this yet, this is in HOD, but it's a set by the separation axiom in V. So it occurs somewhere in the V hierarchy. So then we're going to have U is A relativized to HOD intersect X if and only if V gamma thinks that U is the collection of things in X such that phi Z Y vector holds in HOD. So this is because anything that V gamma thinks is in HOD is in HOD. So the things X is an element of HOD, so it's a subset of HOD. So this is just picking out V gamma is just a suitable place to pick out those elements Z in X for which phi holds relativized to HOD. So what we have here is U is definable over V gamma. So U is definable over V gamma using phi in these parameters. Y vector here. Oh, and X, because it's talking about X. Okay, so this doesn't quite yet put it into OD, because when we define things using, to show that they're in OD, we're only allowed to use ordinals. But this didn't say anything that y vector should be ordinals, and x may certainly not be an ordinal. So we can turn this into a definition which is about ordinals by replacing these objects by their definitions. So we can replace them over here. By their definitions from ordinals. Maybe that sounds a little bit vague, but for example, let's suppose there's only one y for simplicity. It's just some y, one single y. Then there are ordinals, some psi that defines y, and there are some ordinals, alpha y1 up to alpha yn, that define y in OD. So it's the unique set, so that psi y holds of these alpha y vectors here. So it's the unique set Z, such that this holds here. So this is what I mean by saying y is definable using ordinals and some formula. Right? So in here, in this definition, I got this parameter y. But I can replace talk of y by talk of these ordinals, alpha, by just saying, what I mean here is the unique set such that psi z and these ordinals. So in phi z y, we can substitute the definition of y from ordinals for the occurrence of y here. I mean, to spell it out further, right? I can just say something like, okay, there is some z, but not use z, use something else. There's a t such that psi y t, this alpha vector here, and phi z of this t. So this is equivalent to phi z y, right? Because the only thing that makes this true is y by design. So if this formula is holding, this is equivalent to this here. But over here, I've removed mention of y. I've just replaced it by a longer definition, but with these ordinals in. So anything that's in OD, I can always substitute it in a formula by its definition, which used those ordinals, by using this kind of maneuver here. So I can just think of this formula as being replaced by something more complicated, like down here, but only refers to ordinals. So in short, we can replace phi z y vector over here by a longer formula involving ordinal parameters rather than the set parameters that we used in the term A. So the upshot of all of this, right, is that now I've got a definition of U, right, from gamma, whatever ordinals I need to define this y vector here. And I've got then that U is precisely this, right? Hence U will be an OD here. And so U is in HOD because U is a subset of X. And this itself is contained in HOD. So here I'm using that exercise that I started out with, right? To be in HOD means you're in OD, but all of your elements are in HOD. So again, appealing to for exercise 418.1. Okay, let's, because this is exhausting, let's just skip a replacement, just consider that done, and just mention choice. So I'll just say C notes. And the axiom of choice, which after all is one of the main original features of HOD, right, is that again, like L, there's a global well ordering. There's a formula that will define a well ordering of the whole of HOD. And actually, we don't have to do anything for this because we've already seen that there is an ordering of all of OD definable by a formula. So we just use that. So we have a global form of the axiom of choice, just like L. We have a definable well ordering less than OD of all of OD. And this was 423. But HOD is contained in this. So I can just restrict this global well ordering to HOD, to things that are in HOD. Restricted to HOD. So I don't have to do any more work here because I already did it, showing that there was a definable well order OD here, just as we had this definable well order of L here. What you have in the notes is the statement of the axiom of choice for any particular set, or rather the well ordering principle for any set. I could take any X in HOD, right, X is a subset of HOD. So I can just take the restriction of well, X cross X, right? This then is a well order of X. So we have the well ordering principle. Right? Any set X can be well ordered. And that's equivalent to AC, the choice function version of the axiom there. Okay, that's enough of that. So with some labor, we can verify all of the axioms of ZFC inside HOD. Yeah. Okay, let's just look at a few properties of this, and then we'll call it a day. Right? So in fact, OD is kind of a strange creature, right? We've got that any ordinal is in OD. In fact, any V alpha is an element of OD. It's definable from the ordinal alpha. It's the collection of sets of rank less than alpha. Right? It's the unique set satisfying this definition here in the parameter alpha. So all of the V alphas are in OD, but if OD is not transitive, then OD will not necessarily be, well, it will not be V. Right? Just because V alpha is a member does not mean it's a subset. It's not a subset of OD. That would make it HOD. So V alpha intersect OD, right, is a member of OD. Again, it doesn't imply that it's a subset, right? It just means that the OD definable elements of V alpha form an OD definable set. Okay, why? So let Z be the set of Y in V alpha such that there is a gamma such that Y is a member of anything outright definable over V gamma. I mean, this is just saying Y is in OD. OD is the things that are outright definable from an ordinal. I mean, outright definable over a V gamma. But this is just this here. So here is an outright definition of Z, right? And Z equals V alpha intersect OD. So the situation is slightly this OD is a kind of a strange creature on the whole. Let's look at this 420. So the following are equivalent. V is OD, V is HOD, OD is transitive, and actually, perhaps more extreme, the axiom of extensionality holds in OD. So actually, if V is not OD, the axiom of extensionality fails in OD. It's not a transitive class. So most of these things, well, a lot of these things are observations. Okay, so we do a cycle of implications. So 1 implies 2 is trivial because HOD is a subclass of OD. So if, sorry, that was the wrong thing to say. No, that's just the definition of something to be in HOD means it's in OD and all its elements are in HOD. So 1 implies 2 is just the definitions of OD and HOD. I mean, if 1 holds, everything is OD. So it means everything is HOD. Pick any set, it's OD and all of its elements are in HOD. Or pick a set, X, and its transitive closure, all of its things in the transitive closure in HOD. So X is in HOD. Two implies 3. HOD is contained in OD, is contained in V. So if V equals HOD, then OD is V, is HOD, and is transitive. So again, it's kind of trivial. Implies it's transitive. Sorry, 3 implies 4. Here. So we assume it's transitive. Well, if it's transitive, we've said before many a time, any transitive class is a model of the axiom of extensionality. So that's all that needs to be said there. And the last one is the one which has perhaps any bite to it. If the axiom of extensionality holds, it's everything. Okay. So we saw the alpha intersect OD is in OD. And also I said V alpha is in OD. So if V alpha is different from this, meaning there are some things, all that can happen is there's something in V alpha that's not OD, if V alpha is different from this. So if one failed, for some alpha, this might happen. There'd be things in here that are not OD. So if V alpha is different from V alpha intersect OD, we're allowed to use the axiom of extensionality. I've got two things in OD, but the axiom of extensionality holds in OD. So OD sees that there is some difference between these two. So axiom of extensionality holding in OD implies that there is some x in OD which is in their difference. So that this means x is either in V alpha but not in V alpha intersect OD, or the other way around. But not in V alpha. But these facts are contradictory. X is supposed to be in OD, right? So it can't be in V alpha intersect OD but not be in V alpha. But nor can it be in V alpha intersect OD, then it's in V alpha, so it can't be not in V alpha. So this is nonsense here. So there's nothing in here, in this different set here. So V alpha equals V alpha intersect OD, right? So OD contains V alpha. Alpha was general. And this is 1. Okay, let's just then, okay, let me just say then, this of course brings us to the end of the course. You may be pleased to know that actually I decided that this stuff on ordinal definable, heritage ordinal definable sets, this won't be on the exam. So this last week's work here is just really from some interest's sake to show that there was another model besides L in which the axiom of choice held, indeed in this global form. So that finishes our study of that. I will set, if you're interested, I will set some exercises tomorrow just on this work if you want to have a look at it. And of course, there'll be solutions then there as usual. So next week is the revision and stroke problems classes. Right? So what I decided to do was think that this is best done when we're kind of online. Right? So the first, what would have been the first lecture next week, right? It would be best done if this was a problems class. So what I'll do is if anybody sends me some queries, or if anybody says they want something explained or some exercise, right, done, If they send me that over the weekend, then I will talk about that, without your presence and record it. And that will be uploaded as the first of the revision sessions next week. Right? Otherwise, if nobody does send me anything, then what I'm going to do is just have us meet again online during the lecture times of next week, which would be Wednesday and Thursday. And then we would meet again on Friday of next week. So there should be 3 online kind of in real time sessions with me next week. So to repeat, if there's something that you want, particularly if there's some theory or some exercises that you want done, and you send me by email over the weekend what that is, then that'll give me something to talk about in a pre-recorded lecture that I can put up on the YouTube channel for next week. Otherwise, the first time we're going to actually meet in person will be during the usual lecture, which is next Wednesday. All right. Okay. Hope that made sense. And I'll see you then next week. Okay. Bye.